Good morning, everyone. So I think it's time to start. So my name is Sébastien Lebeg. I'm a research director at the LPCT laboratory, and I will act as the president of the committee today for the PhD defense of Thiago Trevizam Dorini. So I will briefly introduce the members of the committee. So we have two referees. The first referee is Miss Anne Emmerich from Toulouse, who is a CNRS researcher. I think that she can hear me well, hopefully.
Yes, perfectly.
Okay. The second referee is Mr. Jacek Goniakowski, who is a research director at the ENSP Sorbonne University. We have also two examinators. I'm never sure if I should say examinators or not. I don't know if it's an English term or not, but okay. So we have Mr. Stefan Forster, who is a researcher at the Institute of Physics in Halle, Germany. Welcome. And we have Miss Céline Dupont, who is CNRS researcher at the ICB at the University of Franche-Comté. And we have also a person who is invited to attend this defense, with Mr. Anton Kolkaj. Sorry, I think I mispronounced your name.
It's okay. It's okay.
Okay, it's not too bad. Okay, thank you. Who is a professor at Ljubljana in Slovenia. And we have also, if I'm not forgetting, no, we have also Miss Emily Gaudry, who is a professor here at the University of Lorraine, and who is the supervisor of Thiago. And myself, as I said, I will be president of the sole examinator. So Thiago, now you have about 45 minutes to present us your work, and then there will be some questions and discussions. So please.
Okay. Well, thank you very much, the president of the jury, for this kind of introduction. I thank you very much all the members of the jury for being here in presence and online, for accepting to be part of my committee. And it's my great honor to present to you my PhD work, which is called Theoretical Investigation of Surfaces and Interfaces at the Atomic Scale, ultra-thin films supported on metals and intermetallics. My name is Thiago Dorini, and my work was supervised by Professor Dr. Emily Gaudry in collaboration with Dr. Anton Kolkaj from Institute Joseph Stefan. So I'd like to start with an introduction of this work on the type of material that we'll be dealing with, which is two-dimensional, ultra-thin two-dimensional materials, which are materials that are materials that have a sheet-like structure of only a few atoms or even one atom thick. And there are some of the famous examples of these materials are graphene, transition metal dechalcogenides, perovskites, layer metal oxides. And what makes this kind of materials apart from all the others are specifically their high specific surface area. They are susceptible to electron confinement in 2 dimensions, and their electronic structure features are very sensitive to external stimuli, to chemical modifications and mechanical deformations. So you can tune their properties to apply to a specific kind of application. And to be even more precise, the type of material that we'll be dealing with are ultra-thin oxide films when supported on a metallic substrate. So here, as you can see on this sketch, we have a ultra-thin oxide film in red of thickness of about 0.2 to 1 nanometer, supported on a metallic substrate. And as we all know, bulk oxide is usually an insulator or a semiconductor. But when you reach the ultra-thin film limits and you support it on a metallic substrate, there is a significant charge transfer between these two materials. And this leads to many unexpected phenomena that happens due to this strong interaction. And this kind of material, they have some really interesting applications, such as electronic devices, gas sensors, and catalysts. And here I'd like to highlight some of the famous examples of these phases. The first is aluminum ultra-thin oxide film deposited on nickel aluminum 110, as you can see on the first image on the left. So it's interesting to notice that the structure of this phase changes completely from the bulk material. And this happens for many, many cases. This happens also for this ultra-thin vanadium oxide when supported on palladium 111, that the structure of these oxides also change considerably when you change the vanadium coverage on these oxide films. And lastly, what I show you here is the first discovered oxide 2D oxide quasi-crystal when supported on platinum 111, which was discovered by the group of Dr. Fuster in 2013. And I'll be discussing in more detail this structure later on this presentation. So these 2D materials, they have a very kind of simple way to describe their 2D structure, which is in terms of the building blocks for its structure. So as you can see, there are many different ways to tessellate the plane and to create this structure. Here I highlight some of the examples, such as we can have some triangles, rectangles, or even structures with only squares. And it's interesting to notice that the type of tiling elements that you have on the structure also correspond to the oxidation state on this part of the structure. They change considerably where you are on this structure. And to complicate even more, the type of the tiling configuration also changes according to the epitaxial relationship with the metallic substrate. For example, you have a different set of oxide formation when you have a metal when this oxide is supported on metal 101, then when you have on a metal 100, as you can see on this image. So as you see, there is a huge number of possible configurations that you can have on an oxide that depends on the oxide composition, its epitaxial relationship with the metal, the temperature and pressure conditions. And we would like to discuss a bit more how we can determine and even predict the structure of these ultra-thin oxide films. So here I would like to highlight two of the main strategies that we have used on this work. So the first strategy is to use a specific set of atomic decorations for each building block on these oxide films, which will use this approach for the first part on oxide quasi-crystalline approximants. And the second strategy is a more brute force approach in which we use a genetic algorithm, and we use this methodology to study some ultra-thin indium oxide films supported on palladium indium 001, which will be the second part of this presentation. So here, I show an overview of my presentation for today, which is the first part. We'll be dealing with oxide quasi-crystalline approximants. I'll give an introduction, discuss the methodology that we've used, and it's separated into three results parts, which will begin by discussing some of the main properties of the sigma approximant phase by using the model that was proposed by Fuster. Secondly, we'll do a similar study, but using an alternative model that was determined by Cocaine and his group. And finally, we'll try to determine which is the correct model to model these phases and apply this to many other approximant phases that have been discovered in the literature. For the second part, we'll use evolutionary computations to study the structure and properties on these indium oxide films supported on palladium indium 001. I'll also begin with an introduction, methodology, and it's separated into four parts, which will discuss the structural prediction. We use ab initio atomistic thermodynamics to study the surface free energy of these phases and try to determine their stabilities. We'll discuss in detail their structure and chart analysis distributions. And in the end, we'll create a database of STM images so that we can compare with experiments in the end. I'll finish this presentation with just some general conclusions and give some perspectives for this work. Let's begin with the first part on oxide quasi-crystalline approximants. And I'd like to introduce how we discovered these oxide quasi-crystal materials. And it began with the study of the barium titanite system. And this is a very important phase, specifically for electric ceramics. This phase has a tetragonal tetragonal structure. And it's interesting to notice that it presents ferroelectricity, which is why this phase is so interesting to study. And of course, it's thermodynamically stable. In this work, Foster and Vidra, they were studying the surface structure of these the surface properties of this phase when supported on a palladium 101 system. They use specifically palladium because it has a very small lattice mismatch with the 101 orientation of barium titanate. And for everyone's surprise, when you heat treat this sample at 1250 Kelvin and ultra high vacuum, there's a very unexpected phenomenon that was a complete change in the structure of this perovskite, and was a discovery of the first oxide quasi-crystal, in which is a 2D material. And it's interesting to note that it has a sharp 12-fold diffraction pattern, as you can see here on the SM image, and it's composed of these three tiny elements specifically. You can see there it's composed of squares, equilateral triangles, and 30-degree rhombuses. And the structure of this quasi-crystal can be represented by the famous CA Nizek-Gehler tiling, the NGT, as you can see on this image on the right. So here, when we try to study this phase, there are mainly two problems that arise. First, since it's a quasi-crystal, we need to deal with how can we study the system using, for instance, methods that need periodic boundary conditions for such a system. And secondly, we do not know the actual structure of this phase, because we only had the STM image. So we start with the first problem, and I would like to start with discussing what is an approximate phase. So an approximate phase is a periodic arrangement of the characteristic building blocks that are inherent to the quasi-crystal. And because they have the same building blocks as the quasi-crystal, their characteristics are also similar to this quasi-crystal. And now, because they are periodic, they present translational symmetry, and we can apply some methodology that needs this kind of property. And here I'd like to highlight the first discovered approximate phase for these systems, which is this phase, the sigma phase. And Fuster and his collaborators determined the first model for the structure by using synchrotron X-ray diffraction. And this is what is the initial structure. And it's interesting to highlight, in this case, in this model, they consider that what we see on the SM images corresponds to the tidings of the titanium atoms, as you can see, corresponds to these squares and triangle, equilateral triangles. In addition, there's a second alternative model for these phases, which was derived by the work of Cocaine, which will have these three tiny configurations. And in this case, what we see on the SM images are the electronic density of the barium atoms. So I'd like to highlight, we have seen that we have the perovskite structure in these phases. We have the oxide quasi-crystal. We have a competition between these phases also with many other approximate phases. I've shown only one, but there is also a giant approximate, an hexagonal, a monoclinic, and some other phases, approximate phases that have been discovered. In addition, for lower contents of barium, there is also a honeycomb phase that can be formed. As you can see, here we have an STM image in which you can see the hexagon honeycomb structure of titanium oxygen lattice, where barium is located in the vacancies of this lattice. So after introducing this system, I would like to show the objectives of this first part of the work, which is first, we'd like to determine some general properties of these phases by using first the Fuster sigma model when changing the composition for the alkaline earth elements, the transition metal, and also the metallic substrate. Second, we would like to study in depth especially the interface between the sigma phase, but using now the Cocaine model on the strontium titanate oxygen system when supported on platinum 101. Based on this study, we would like to determine which one is the correct model for these phases. And in the end, we'd like to use this model to calculate the electronic properties of many other approximate phases that have been discovered. So the methodology that we use with density functional theory with the VASP code, which use the plane wave basis sets and the Paul method. We have coupled all calculations with the atomic simulation environments so that we can facilitate a bit all our calculations in post-processing. We have used the PBE van der Waals functional, and these are the characteristics for all these calculations. The substrate was modeled with 4 layers of metal 101, with 20 angstrom of vacuum, and with the dipole correction. In our case, since we have the very localized electrons from the deep band of the transition metals, we had to use an approach. It's called the DFT plus U. And in our case, we use the Dorini approach. In this approach, we need to add a correction term to the total energy of density functional theory, as you can see on this first equation. And this correction term has use this formula, in which we need to calculate the U effective for this correction term. In our case, due to the similarities with our system, we have used the U values that were determined by Gunakovsky and his collaborators in this work. And our calculations were done in these three supercomputers, Explore, Janzé, and Oxygen. So I'd like to start with the first part of the results on analyzing the general properties of the Fuster sigma model when supported on platinum on three different metals and changing composition of the oxides. Here you can see all the composition that we have selected. This is green for the alkaline earth elements, all the transition metals, and the substrates. And in total, we have calculated for 63 compositions. So to begin with, the structural relaxation for all these systems, we have seen, especially that there's a great influence, especially of the transition metal in the overall oxide relaxation. And here I would like to highlight the first property, the rumpling, which is given by this equation, which is the difference in height between the cations and anions in the oxide. And as you can see, when we increase the electronegativity of the transition metal, there's also an increase of this rumpling parameter. And this may correspond also to a increase or a very different set of the charge distribution on these compositions. And we'd like to measure this with a methodology that's called the Bader charge analysis. In this analysis, what we do is partition the density according to zero flux surfaces. And in this methodology, we can have the electronic charges on individual atoms on these oxides. And here we plotted the same rumpling parameter, the same structural parameter, according to the Bader charge on the transition metal. And we can see that there's a fairly really linear relationship between how the oxide relaxes with the charge on this specific metal. And also this corresponds to an increase also in the adhesive energy between the oxide and the metallic substrate. We have calculated adhesive energy with this equation. And you can see that the oxide bonds more strongly with the substrates when you have this characteristic on the rumpling. And we see that this all corresponds to how the charge is being concentrated or distributed in the transition metal. Okay, so at this point in our work, there were several debates between our group and many other groups about what is the correct model for these oxide phases, for these quasi-crystals. And the question was if this model that was firstly obtained by Fuster was the correct one with the titanium atoms at the vertices, or the cocaine model, which has the barium atoms, or in this case, the strontium atoms in the vertices. So I'd like to highlight some of the characteristics of these phases. First, if you look at the entropy formation for these two models, the cocaine model is a bit more stable. In addition, the atomic density, as you can clearly see, is higher on the cocaine model. This may correspond also to a decrease in the surface free energy of this phase that may lead to stabilization, to its stabilization. And also the adhesive energy of this cocaine phase is stronger than on the Fuster sigma model, so which lead us to believe that this phase this model may actually be the correct model to build the approximate phases. So now what we would like to do is use this model to understand their characteristics, specifically at the interface between this oxide and the platinum substrate, and the stability of this phase. And I'd like to start with a very general property, which is the charge density difference. In this case, what we can see in blue, we have the charge density difference in the oxides, and we see that the oxide is actually donating the charge, especially to the interface region and to the first layer of platinum. And we can see on this 3D image, we can see the same characteristic, but it's interesting to notice that due to the oxide relaxation, the titanium atoms are moving closer to the platinum substrate. And we can see that it may have been the titanium atoms that are donating the charge, especially to the platinum first layer. which leads us to believe that first the bonds between the oxide and the substrate may come from these bonds, specifically the titanium and platinum, and the overall oxide stabilization may also come from this bond. So I would like to study more in detail the bond between titanium and platinum at the interface. And for this, we have used the crystal orbital Hamilton population. In this methodology, what we do is we divide the density of states in terms of the bonding and anti-bonding characteristics for each bond. And here, for the titanium-platinum bond, we have made the average of 17 bonds in this system. And here we have the results for this analysis. So how can we read this graph? In blue, we have the bonding states for these bonds. And in gray, we have the anti-bonding states. And as you can see, for the occupied states, for all energy levels on the occupied states, we have only a bonding characteristic for this bond, and we have the anti-bonding character only for the non-occupied states. Which leads us to conclude that there's a very strong titanium-platinum bond at the interface. And we'll also like to see about the bonds, not only at the interface, but also if this corresponds to stabilization also on the oxide. So here I have highlighted the COHP analysis on the titanium oxygen bonds on the oxide and also strontium oxygen bonds. And we can see that there's also very stable and very strong COHP analysis, very strong bonding character of these bonds for both of these analyses. And this system was when we have platinum, when the oxide was supported on platinum 1-on-1. And if we do the same analysis, but without the platinum substrate, it's interesting to notice that there is a significant decrease in the bonding character for these two bonds. And even for the strontium oxygen, there's not even a bonding character anymore. So this leads us to believe that the titanium-platinum bond between the oxide and the substrate not only corresponds to the stabilization of the oxides at the interface between their adhesive energy, but also can correspond to the stabilization of the oxide in general. So we have seen that this model might be the correct one, might be the most suitable model for these approximate phases. And we would like to model some other approximates using the same timings. And here I show you one of the other approximates that were discovered, which is the giant square approximate. It was discovered by a group here in Nancy by Dr. Vincent Fournet and his group, and independently discovered by Schenk and his group in this recent work. And here we have the structure of this approximate phase, which is a giant square because it is a really big structure of 44 by 44 angstroms. And it presents the three tiny configurations, the square, triangles, and rhombuses. And when we use the model by Cocaine with these three tiny configurations, we can create this approximate structure. In this case, we have selected to model this structure with 3 layers of platinum due to its bigger size. And it has similar relaxation characteristics as we see that the titanium atoms move closer to the platinum substrate and the oxygen and strontium atoms move upwards. The same analysis were done with another phase that was discovered, which we call the large hexagonal phase. It also presented 3 tiny configurations and basically the same relaxation properties as the other approximate phase. And it is interesting to notice that the difference between these 2 phases with the sigma approximate is that there is in these 2 phases, there is the rhombus tiny configuration, and the sigma phase, it's a smaller phase, and it presents only triangles and squares. When we simulate the SEM images for these 2 phases and compare with the experiments that were done by the group of Professor Dr. Vincent, in gray we can see this image that we have simulated, and in orange you can see the experimental image, and there is a perfect match between these 2 images that corresponds. In the end, we have seen that it corresponds to the electronic density of the strontium atoms in this system, not of the titanium. And this also leads us to believe that the model by Cocaine was the correct model. And finally, I would like to highlight one interesting property of these phases. When we calculate the adhesive energy for the 3 phases, its adhesive energy, increases when we also increase the amount of titanium in each of these, the amount of titanium per angstrom square in each of these approximate phases. And this is consistent with the COHP analysis that we have done for the cocaine sigma model, where we have seen that when you have more titanium bonded to the platinum atoms, it may correspond to a higher adhesive energy between the oxide and the substrate. So far I've shown only 3 phases, 3 approximate phases, but there is at least 12 periodic phases on this system that have occurred so far. And the tiling configurations can be more varied other than rhombus, triangles, and squares. But the question that we asked ourselves is what makes this the approximate that were discovered experimentally so special in relation with some other approximate that were not discovered? Because when you look at the NZT tiling, there is an infinite amount of approximate phases that you can form depending on how you select the structure. But what makes these structures so special? So we would like to just try to analyze this question by selecting a few other approximate phases that we can find in the literature. 2 monoclinic phases, 1 small hexagonal phase. This phase is on another system, but for the comparison sake, we have also used this phase for the same strontium titanite over platinum 101. And we have selected manually 3 approximate phases to compare with these other approximates. As you can see, the approximate 1, approximate 2, and approximate 3. And here are some general properties for all these phases. Well, it's interesting to notice that we did not find any particular difference in relation to the structural relaxation or the charge distribution of these phases. As you can see, for all these phases, their parameters are basically done out very significantly. What actually changes is first the adhesive energy, as we see that it depends on the amount of titanium per area on these oxide approximates. And also the enthalpy of formation vary also considerably depending on the composition. And we can see that there's, for the 2 manually discovered approximates, approximate 2 and approximate 3, it has the lowest enthalpy of formation, even lower than the 2 of the discovered approximates, the giant and the hexagonal, which leads us to believe that there may still be many other approximate phases yet to be discovered. So this leads us to the first conclusion of this, the conclusion for this first part, which is we successfully determined which is the best model to represent these oxide quasi-crystalline approximates. We see that the titanium atoms specifically bond strongly with the metallic substrates based on COHP calculations. There were a great agreement between the simulated and experimental SCM images used in this cocaine model. And there may still be some other yet to discover approximate phases. So here I would like to pass to the second part of this work. On this first part, we have studied a system that is very, very interesting, very complex. These materials are very hard, very difficult to make. And what the application of the material not yet been fully understood. And here for this system is much more simpler. And also there is a very specific application that we can use these materials, which is on methanol formation. Well, methanol is a very important molecule for the future of energy because it's a molecule that you can store in a liquid form, and you can get hydrogen from this molecule by using the reverse water gas shift reaction. So here I highlight one of the processes that you can use to form methanol. In industry, well, you have many gases that are byproducts of many reactions, such as CO, CO2, or even H2. And you use this general copper-based catalyst to form methanol. The problem with this catalyst is that it's very low in CO2 selectivity, and there's also many byproducts that form, especially CO, to this reverse water gas shift reaction. And in the literature, we can find an alternative material that seems to be much better than this copper-based material, which is the palladium indium, the indium oxide supported on palladium indium system. This system has a much higher selectivity and activity for the production of methanol. And we have, so far, we do not know exactly why this system is so good for its catalytic properties. There are many studies trying to understand what's happening, especially this work by Kowitsky. and collaborators, in which they have identified that especially one of the main parameters that may lead to these great catalytic properties on this material may come due to the interaction between a thin layer of this oxide film and this palladium indium substrate. So this leads us to, or one of the objectives of this work is first try to understand what is the structure of this oxide supported on palladium indium one-on-one, and also try, after selecting what is the best structure, we would like to determine their stabilities, electronic properties, and also create a database of STM images so that future experimentalists could compare. For the second part, we have also used density functional theory with the vast code, also combined with the atomic simulation environment. In this case, we have used the PBE functional, and these were the characteristics for these calculations. For this case, we have modeled the substrate with 10 layers of palladium indium 001, and we have used fixing angstrom of vacuum with the dipole correction. We have used for these calculations 3 supercomputers, the Explore, Topaz, and Irene. So in this case, we need to search in a very big configurational space, and there are several methodologies that we can use to do this, to search for this. There are Monte Carlo simulations, molecular dynamics, and in our case, since we have a huge configurational space, because we have we'll change the substrate size and also change the oxide composition, we have chosen to use a genetic algorithm with the USPEX code. So here we have a small recipe on how we did these calculations. First, we generated randomly the structures, and we ranked the best structures based on this first generation according to their total energies. After, we have used some variational operators to create a new generation based on this old one. We have used these 4 variation operators to change between generations. And the simulation ends when the halting criteria is met, and basically when the next generation is the same as the old generation. But to be more specific, here we have the system that we have used. There is a palladium indium substrate and separated into several regions. The first one is the fixed atoms. The second one is the buffer atoms, which we allow them to relax alongside the oxide. We have the surface region where we deposit the indium and oxygen atoms. And also there's the vacuum region. To be a bit more specific, for this substrate, we have selected 2 types of terminations. First, we have fixed the palladium termination and added the indium and oxygen indium and oxygen at the surface region. And secondly, we also fixed an indium termination and added an oxygen add layer. So in this case, we have chosen to use 3 supercells for the substrate. Here we have a 1x3 substrate, but we also use a 1x5 and a 1x7. And we have chosen several compositions for the indium oxide system that range from about ENO to EN203. So here we have a summary on how we will do these calculations. So we'll use a genetic algorithm to build the structures, use standard DFT to optimize them, and at the end, we'll calculate the electronic structure features by using a code that we have developed in our group. So here we have the results for the end-up formation. All the phases that we have calculated using the USPEX code. So you can see that there's more than 100,000 structures. And as you can see on the graph, these 3 interperformations graph, the 1x3 results, 1x5 and 1x7. And based on an energetic criteria of 0.1 electron volt per atom, we have selected 114 best structures to study in more detail. So from now on, just to be a bit more concise, I've separated structures for 1 to 29. It will be structures that are 1x3, they're smaller ones. 30 to 46 are 1x5 structures, and 47 to 114 are the larger structures, the 1x7. After we have chosen which are the best structures to study in detail, we have increased the precision of all our calculations, and we have redone the interperformation for these phases. As we can see, there is a negative interperformation for all these phases, which is a very positive for us. That means that all these phases are stable. the most negative ones present an composition that are a bit deviated from the ideal EN203. And from this, you can start to see what are the tiny configurations that we see on these oxides. First, I've separated into 4 structures. The first one, we have formation of hexagons on the oxygen timings. We have also some rectangles. We can also have a combination of both of these 2 timings. We can also have these 2 timings, and we also have some structures that present some holes in its structure, especially the bigger 1/7 ones. So here we have only studied the interperformation for these structures, so we cannot compare directly which is the most stable than the other. So I'd like to use a model that's called the surface, which is called the ab initio atomistic thermodynamics, to study in detail the surface free energy of these phases. So how can we use this model? So this methodology we use, we obtain the temperature contribution by taking into account explicitly the gas phase. So in this case, we expand the partition function of the oxygen molecule in terms of the translational, rotational, vibrational, and electronic features. And here we have a model of this system. So we have our metallic substrates with the oxides here. And also we have on top, we have a reservoir of oxygen molecules in contact with this system. And by using the methodology that was proposed by Rogel and Reuter in their famous paper and applied to our system, we have this equation to calculate the surface free energy of our structure. And we can have the temperature and pressure contribution by expanding the chemical potential of the oxygen molecule, the O2 molecule. So here we have the first results for all 114 structures at temperature of 300 Kelvin in 1 ATM. If we zoom at the most stable structures, it is interesting to notice that the structures that have the lowest interperformation usually also present some of the most stable surface free energy, with a few exceptions, such as structure 27 and 63. When you increase the temperature on this model, there is an interesting shift where some of the bigger structures, the 1/7 structures, start to become more stable than the smaller 1/3 structures. As we see at 1200 Kelvin, we have the structure 63 being the most stable of all the other structures. And in order to compare with this methodology, we have created a separate, different model, which we call the grand potential model, which we use this equation that was based on work by Gao and his collaborators. In this case, what we do is we also consider that the oxide within film is also in contact with the metallic bulk, with a bulk EN203. So here we have the results for this using this model. We can also see that the structure that has the lowest interperformation also present a very stable grand potential free energy. And we can see that the structures, there's a tendency that the structures that are bigger to be more stable than the structures that are less bigger, the 1/3 and 1/5. And this also, we can also see this property when we increase the temperature, where the 1/7 structures become even more stable than the smaller ones. So here we have seen this their stabilization only by a thermodynamic approach, but we will also this methodology with the structure and some electronic property, some electronic feature of these phases. So I'd like to study their structure and electronic properties in a bit more detail. So here I've highlighted 4 structures that corresponds very well to what's happening to the surface stabilization of these phases. The least stable structure, as you can see on the top, it has only this first tiny configuration, this hexagonal tiny configurations, with a lot of holes in this structure. When you decrease the number of holes, you stabilize the surface free energy. When you remove all the holes, you stabilize even more. But in this case, the hexagons become a bit distorted. And when you combine the hexagons with the rectangular timing, you have the most compact oxide structure. And this leads to a more stable surface free energy for these oxides. And this approach can be used for all the other oxides that we have studied. So in addition, we have also studied the charge distribution of all these phases. So what we have done here, we have on the left, the butter charge analysis on the palladium atoms on the last layer that is in contact with the oxide, with the rumpling, which, as a reminder, is the difference in height between, in this case, the indium and oxygen atoms. And it's interesting to see that we can separate this structure into 4 different categories. The first one, there are some structures in which there was the formation of O2 molecules, as you can see here. The second one, the purple one, is where we have some structures that I said that they exploded. That's basically the oxide is not, there are some atoms that is not in contact with the substrate anymore. And there is also the intermediate structures, which separate into 2 groups. And it's interesting to see that the most stable surface free energy structures have a specific part on this graph. They are all located on this region, which leads us to believe that a real oxide that can form may have this charging configuration on red, as you can see. In addition, we have simulated the SEM images for all the phases that we've calculated, so that we can see what are their properties. And we can see that what you can see on the SM image is the electron density of oxygen and indium atoms, specifically 2, because we can see that there's a non-zero local density of states at the Fermi level in these phases. And well, this happens specifically, as I said on the beginning, due to the charge transfer between the metallic substrate and the oxide. And more precisely, the bright spots that we see on the SM images corresponds specifically to the electronic structure of the protruded oxygen atoms, because they are above the mean surface free mean height plane of these oxides. So it's easier to see the electronic density of these atoms. Which lead me to some of the general conclusions for this presentation. For this second part, we have determined the structure of a plethora of ultra-thin indium oxide films when supported on palladium indium 001 with several composition substrate supercells. We have applied 2 different thermodynamic models to study which were the most stable structures. Between these structures, we have found a correlation between the charge distribution and the surface free energy for these phases. And at the end, we have created an SEM image, a database of SEM images, and determined the relationship with the oxide structure and local density of states. For the first part, we have determined which were the most suitable model to analyze the oxide quasi-crystal approximants. We have seen that the titanium atoms, they are bonded strongly to the metallic substrates with the COHP calculations, and this may lead to the stabilization of the approximants in general. We had found a great agreement between the simulated and experimental SM images with this model that was proposed by Cocaine and his group. And we have seen that there may be many other approximate phases yet to be discovered. And here I'd like to highlight some of the perspectives for this work. We have basically seen many of the static properties of these phases, but it will be interesting to expand this to some of more dynamic properties to study in more details using phonon calculations and ab initio molecular dynamics to study their stability and many other interesting properties. And also to calculate some adsorption properties of when you have the 660 molecule on the surface of these oxides and compare with some recent experiments by this work. And secondly, for this second part, it will be interesting to increase the configuration of space to search for these oxide systems, either by using other methodologies or increasing the size of the substrate supercell or increasing the number of oxides compositions. Produce also samples to compare with the SM database that we have, and calculate the catalytic properties of some of the best phases that we have found to compare with the conventional copper-based catalysts. Well, here I would like to thank everyone that have worked with me. It was a great pleasure to work with everyone. It was really, really great. And I thank you all very much for your kind attention.
Thank you for your presentation. So now it's time for questions. So I think we can start, for instance, with a question of Anne. she can hear us.
Yes, I can.
Okay.
Okay. Thiago, first, thank you for this presentation, which was really clear presentation of your work. It is a presentation of quality. It is also a good synthesis of your work, and you have made a relevant choice of some results to present, not to present the whole thing. So congratulations for this. And you describe your work also with an educational way of presenting that raises some of my questions already. So I would like also to mention that you did a real work on this presentation with many figures that are not in your manuscripts. So, okay, so this presentation is also of the same quality as that of your manuscript, which is an easy and pleasant manuscript to read, with many figures and tables that really help to make a nice synthesis of all the materials that you have been able to treat. And congratulations also for this synthesis in the thesis manuscript and for the dedicated work you conduct during these PhD years.
Thank you very much.
So before starting with some remarks, I would like also to thank your supervisor for inviting me to be part of this committee and to be able to discover your work in details. And I would have really liked to participate to this committee in person, but okay.
Yeah.
So
we're really glad to have you here, but well, we understand the situation.
yes, but well, the pity is that this is not due to the weather, only due to the strike. It is a bit, yeah. Okay, so let's move on to some remarks, some questions. I don't have many because for me the presentation was really clear, and there will be more remarks of understanding.
Okay.
So maybe first on the manuscript, you write that an important property is to calculate the surface energy of these assemblies you create. But also an important property is the characterization, the knowledge of the stability of the film, which it seems to me is given by the interface energy.
Yes, but the problem with in our case, it's very hard to try to see the stability specifically by trying to calculate the surface free energy at the interface. We did not find a simple model to do this, so we try to correlate more to the surface free energy than at the surface than at the interface. Okay.
I totally share this technical issue. So, okay, I understand.
Even when I showed the thermodynamic model that we have used for the indium oxide systems, one term that's this surface free energy at the interface, and we have chosen the approximation that this energy corresponds to the adhesive energy of these phases. We have also used this approximation.
Okay, thank you. Also a general question about the procedure of the construction of the slab. So you start from the metallic slab and you deposit your oxide, right?
Yes.
Okay, can you then explain a bit more the procedure for the study of the lattice mismatch? How do you conduct this study?
For which case, for the oxide quasicrystals or the
yes.
Well, in this case, there were two things that we have done. First, we basically have had the experimental parameters for these systems, and we have only built the platinum substrate, and we have put the oxide on top according to the parameters of the experimental parameters. But in fact, we cannot use exactly the same parameter because we need to relax our structure according to a functional that we had. So we try to be as close as possible to the experimental value.
Okay.
And And well, the second thing that appears when we do this is we have another degree of freedom also on how we put this oxide on the platinum substrate. And for this, we have tried to simulate many different translations and rotations on these systems, and we did not find a significant difference in the total energy. So that's why I didn't discuss this in much detail on the work.
Okay. Thank you. It is clear.
No, thank you.
Still on the construction of your box, but today this is not mentioned. For both systems, you mentioned in your manuscript that you use 3 layers of metal, and today you just say 4, but in some place on your manuscript you say that you have only 3 layers. So it was one of my question about the different number of layer you use. But
yeah, in fact, when we studied in detail the sigma phase by using both models, we have 4 layers. But when we compare it to all the other approximate phases that we had approximate that were really, really big, so we needed to decrease the number of layers. We decided to remove 1 layer so that we could compare better their properties.
Okay.
I know it's a bit confusing on the manuscript, but so for the phase we use 4, and for all the others we have used 3. And we have recalculated for the sigma with 3 at the end to compare with the others as well.
And on this big system, did you check the electronic transfer, notably, as a function of the number of layers?
No, for these big systems, no. We have only done this for the smaller systems, and we applied for all the others. Okay,
just to double check about the reservoir created by the substrate, but I can perfectly understand the limitation of this.
Yes.
Okay. Then can you go on slide 22, please? Yes. Yeah, this one. I'm not really familiar with this kind of analysis, but I think this is really interesting, and I would like to know what is the signification of the abscissa axis.
The COHP.
Yes, please. Notably the order of magnitude between the PT, between the TiO bonds and the SRO bonds, because you say that this shows that for both you have a strong interaction, but the order of magnitude between your 2 plots is really huge. Yes,
it's hard. It's a bit hard to measure directly the order of magnitude, because between the titanium oxygen and strontium oxygen, there is a different amount of bonds that we consider. So in one case, there are more bonds that we consider than the others. But this also corresponds that in a way, when you integrate on the bonding region of this for each bond, you have in a way the strength of this bond. So in a way, you can say that the titanium oxygen bonds are stronger than the strontium oxygen bonds. Okay. And this is what you call also in your manuscript the ICOHP, the I? Yeah, I is for integrated, is when you integrate. Okay. So then this is an integration over all the bonds you consider, and when you give the average value in your manuscript, this is only a division by the number of bonds, right? Yes, exactly. Okay. Thank you. You're welcome. Then I will go on the other system, on the indium oxide. Okay. And notably in your thermodynamic equation, my question is, how do you obtain the mu for the palladium and the indium? How did you calculate those values? Okay, so in this case, we need to consider, as you can see on this, on the results, we have some limits for the chemical potential of indium. And these limits were based on the cohesive energy of indium and palladium. So in one case, we consider that the chemical potential of indium is the cohesive energy of indium. And we construct the equation based on this fact. And on the other, we construct the equation based on the cohesive energy of palladium is the chemical potential of palladium. So then we'll have two equations, and we can reach from these two equations this final equation in the end.
Okay, so they have been calculated in bulks of palladium and bulks of indium.
Yes, exactly.
Okay. Okay. I'm not very familiar with USPECs in terms of use. I know a bit about, but I notably wonder about the ability of this tool to explore patterns outside of the algorithm. I mean, outside the pattern you provide as input. Can you comment on it?
Yes, it's a real limitation of USPECs, because, well, in our case, you fix the substrate. We have chosen only 3, so we have this constraint that you only add on this surface region, which is a small region. But we try to compensate with this by changing the composition considerably. So in our case, I think we have a very good range set of structures on the configurational space.
Okay, and what about the choices you made at the beginning of the use? Because you have the 1x7, the 1x5, the 1x3. What about not to choose, for instance, I do not know, 2x2 or something like that, in order to be able to expand a bit in all the 2D dimension? Yeah,
this is a great question. Actually, because we had experimental evidence that the structure might be a 1x7. So we started from this, and we have selected other 1x3 and 1x5. But in fact, we have also, after this, we have also begun to use a 2x2 or even a 2x3. But what calculations were not finished. That's why I only shows this. But it's really a great idea to expand this and try to see some other patterns on different substrates.
Okay, can you go on slide 41? Yes, and notably here you show a trend that going on with larger input pattern allow to get more stable, more maybe meaningful final configuration. So it could be okay. So I wonder about the ability to go on a larger environment.
Yeah. In this specific case, I think that we have a more stabilization specifically of the 1x7. Because the 1x7 we can find more stable configurations on the configurational space than when we are limited to the 1x5 and 1x3. Yeah. And I think if we expand even more to a 2x2 or 2x3, we may also find some similar behavior, I think, because we may also have some oxides that cover all the surface, and they might be really stable as well.
Okay. Notably, in this study, did you try to compare with some known surfaces for the indium oxide, which are the most stable ones?
No, we didn't reach. We did not reach so far. It would be a good idea to test, to try to compare their stabilities with the bulk indium. Yeah. But we didn't reach this point.
Okay. because one of the most stable surface for the indium oxide is the 111, which is notably well known for the gas sensor application. And I was curious in your structure to try to identify some of the pattern of this 111 surface. But here the point is that the reconstruction of this 111 surface is takes place on large motif, so that I do not know if USPEX will be able to obtain this 111 kind of surface. What about learning phase in this USPEX? Is it possible to provide to this tool some structure to try to learn to it some stable configuration or not?
Yes, well, I think not exactly to learn, but you can give some structure that we call the seeds, that you have an idea of what are the good structures, so that you start on this, or in a way you learn that this is the good structure.
Okay.
But I believe that in this case, for this, when you have we have used those specs in our case because our oxide system were relatively small, and the configuration space was really big, but it was feasible. In a case of a more complex oxide structure, I don't think it would, at least with our computational resources, it would be a bit harder to make.
Okay. And you discuss also about the huge computational space you have, and that you have to use critical size. Can I have an idea about this critical size for the study in UPSEX?
What do you mean by critical size?
I mean for the exploration of the chemical environment. Okay, you wrote it on your manuscript. The difficulty of genetic algorithm to sample such a huge configurational space usually needed a much larger set of generation.
Okay.
On page 118.
108.
This is when you form some hole.
108 or 80?
18, 118, the top of the page.
I don't know, I'm not sure why.
You said that you have a huge configurational space.
Yes. Well, I don't know what happened because I do not have the same version, I think. Can you just repeat the question, please?
Okay. In your manuscript, you say that you have a huge configurational space to sample, I guess, with this algorithm.
Yes.
So I guess that you use some descriptor of some way to sample all the local atomic environments.
Yeah, well, okay. So this it's done inside the USPEX already. Because in our case, we do not have any seeds to start the structure, but USPEX, it has in a way, it already has in its algorithm how to select where to put the atoms according to the specific atomic environment. It does not go totally randomly where to put the atoms. So this, in a way, was done already in the algorithm by USPEX. We did not do this.
Okay. Okay, on slide 44.
Okay. Okay.
Yes, I have a question about the typically the configuration you obtain on the left. Did you try to run the stability of this configuration you obtain, removing the O2 molecule which has been formed?
No, we didn't do this.
Mm-hmm.
Because in a way, most of the structures, I believe, well, I didn't test this, but I believe we have many structures that resembled a lot, that in the end, you have only a small distortion or they're very similar. I believe in this case, if we remove, we would also have another structure that would be the same as this one.
Yes, but yeah, this is really I don't know how to say this, because this is one of the operation mode of the gas sensor. Okay. This layer, the oxygen atom from this oxide are really reactive, notably with some gases to react and dissolve, and these oxygen atoms are really reactive. They can be added on the surface and removed on the surface, and this is some kind of catalytic cycle through the reduction or oxidation of the surface. If you do not have any vacancy below, the O2 is not stable at all above this surface. But once you have a vacancy, you will favor the interaction of the O2 on the vacancy. So here, maybe your stability of this system is biased because of the non-favorable adsorption energy of the O2 on the surface. Okay. So maybe you find some good structure for the oxide because you have just too many atoms, too many oxygen atoms on your oxide layer. And if you remove from for the total energy of this system, if you remove the O2, you can improve a bit this energy. And this is really one of the operation mode of the gas sensor. And I think this is really interesting to try this study.
Okay, well,
yeah.
it's a good idea. We'll try to do this to see if there is anything that changes when we remove this oxygen on the molecule.
Maybe because I do not have a look on the oxide layer here, but yes, this is good. I was really pleased to see this.
Okay, thank you for your comments.
Okay, so finally, my last question, maybe a general one, about the positioning of your work. Notably, at the beginning of your manuscript, you write that you want to make a definition and classification of structural motif of 2D ultracine materials. What does this mean exactly? What is the expected goal at the end, notably which property in particular, the structures, the electronic properties? And it's really possible to achieve this with DFT approach and also in an universal way for all 2D materials.
Yes, so I think this is more clearly seen in the second part when we use the genetic algorithm to create many oxides with many configurations. And in a way, we have categorized what is some of the tiny blocks that form a stable oxide structure. And it's easier to have this a database approach when we have this genetic algorithm. In the first part, it was a bit harder because we come from the experiments and we use some specific tiny configurations. So the idea is basically after we have selected what is the best structures, we see that they are stable, and we correlate the tiny configurations that we have selected to according to their structures. That I think in the end, what I'm trying to say is only by looking at the structure of these oxides, especially the indium oxide systems, we could have an idea about their stabilization in many other properties such as the SCM images Probably the charge distribution would be a bit more challenging, but only by knowing the tiny configuration of these oxides may lead us to some properties. So this was some of the things that this is what I meant in the beginning of the work.
Okay. Okay. So that's all to me. Again, thank you for your answer and congratulations for this work.
Thank you very much for your questions and for your presence with us. Thank you very much.
Thank you, Anne. So now let's hear the second referee, Jacek.
Thank you. So thank you very much, Thiago. I will join Anne with congratulating you for the very nice presentation. I think you have chosen the good elements. You have put a nice history that is easy to listen, convincing, and well illustrated with figures.
Thank you.
Very nice.
Thank you very much.
The manuscript is a little bit different because there's a huge amount of data in it. So it was a challenge to put it in the free and be synthetic, easy to follow. And I think you have accomplished it. Even if some parts at the first glance look a little bit like separated papers. Yes. I found later on this synthesis part that nicely makes the links that are necessary to follow and compare them. So this was very useful.
Okay.
And it is clear that with that amount of data, it is not very easy to include everything and the pedagogical legacy. I would congratulate you as well on the scientific content of gone to the most pertinent aspects. So the density of the network, the question of titanium for the stability, and likely this is what is important for the observed structure. And on the other hand, you have used a variety of tools, so more or less standard ab initio, but also this genetic algorithm structural optimization that is much more recent, more challenging. And you have written codes yourself to automatize and simplify the analysis. So I think this is a very complete work beyond just standard application.
Thank you very much.
Congratulations.
Thanks.
Now I will have a few questions. I would perhaps not ask questions about these fuzzy crystals because you will have to specialists later on, so we will have probably the most pertinent questions you have. I would perhaps also have a few technical questions because since I do a lot of calculations myself, I always ask myself questions about how it is done and what are the differences. So let's start with this part on indium oxides. For me, it is not clear. It was not clear in your manuscript, and it was not clear in your presentation if indeed the substrate participate with indium atoms to the oxide layer, because you have considered two situations. For palladium terminated, and you put indium monoxide, and indium terminated and you put oxygen. But this second corresponds to palladium terminated with indium monoxide on top.
Yes.
So in some way they are very similar. So my question would be if the indium would go out of the substrate to create oxygen indium bonds or no? And are the energetics of palladium oxygen and indium oxygen bonds pertinent to decide if it should happen or not?
Okay, but in the first question, you mean if you have the diffusion of indium from the bulk that goes to the surface? So, I'm not sure in this case, because indeed it's interesting to see actually what happens when the influence of the substrate. Because in our case we have only selected one orientation, and we do not know exactly what is the influence of the substrate to the.
But did you let this mechanism occur during your optimization? So was your substrate participating to optimization so that the atoms could move out of the substrate and into the oxide?
Yes, there's the one region that the substrate relax alongside, but at least I've not seen any case in which you had an engine from the bulk that went
Okay,
to
so
the
it
oxide.
didn't happen.
It didn't happen in this case.
And is it expected? What is the relative strength of palladium oxygen and indium oxygen bonds?
I'm not sure because we didn't do this, for instance, the COHP analysis to see the actual strength on these bonds. We need to look in more details for this. I'm not sure.
I will come back to this question later.
Okay.
For the titanium-based oxides. But here I would like to go and have a look at this formula at slide 41. This grand potential formula.
Okay.
I'm not sure if I understand it correctly, but you need to divide this energy difference by the number of atoms and by the area. So if you make a Gedanken experiment, you take a 1-by-1 cell with your oxide, and it happens that it has just one atom. Okay? And then you do exactly the same calculation in the 2-by-1 cell. You would expect to find exactly the same energy. It is exactly the same structure. But you have two atoms, and you have the area that is twice larger. So you divide by 2 and by 2. You will not find the same thing.
Okay.
That'll be a factor too many.
I'm not sure if I understood correctly, because when you divide by the area, you would have a more general thing when you divide by the area for different substrates, so that you could compare. In our case, we want to compare the 1/3, 1/5, and 1/7. So that's why we needed to divide also by the area. Otherwise, it would not correspond to the same thing, I think.
And I think if you divide by both the number of atoms and the area, then you obtain this kind of decreasing behavior with a size of your unit cell. That might be not fully physical.
I see. Well, in our case, since there are a few exceptions, such as these structures. Yeah, I'm not sure if this would be a problem or not in this case.
It's perhaps worth testing, because typically if you use a 1/6 unit cell, you can reproduce the same structure twice in 1/6. And you can calculate using this formula the energy and see if you obtain the same thing.
Okay.
Not 100% sure if it will happen.
Okay.
The other formula, I think I have a problem, but it might be just a naming convention. Especially that you say that you approximate interface energy with adhesion energy. I was always taught that interface energy is the sum of surface energies minus adhesion energy. But this is just perhaps in the naming convention, because otherwise the formula looks all right.
Yeah. Yeah, in our case, we do not know exactly what. After you, if you please, you can show me where you find this correlation, because I didn't find exactly one simple way to calculate this interface energy. So we try to approximate this with one parameter that's easily to calculate. That's
I think the relationships between interface energy as a sum of surface energies minus adhesion is standard textbook.
okay.
Okay, so these are such a little technical aspects. Now, for me, the question is why? Because the indium oxide crystal, it exists as the corundum and Bixby, I think, polymorphs. And if it is corundum, you would expect to have the honeycomb rings, you know, such as 6-membered rings. And they do not appear in your case. In addition, they have a good stoichiometry, whereas what appears in your story is a lot of small rings, but in fact has a wrong stoichiometry because they have this induced oxygen ENO stoichiometry. So the fact that these bigger honeycombs do not appear is just because your unit cell is not large enough, or for some other reason.
I think this is the case because our unit cell might not be large enough. I think if we had a 2x2 specifically, it would be easier to find a honeycomb structure.
Okay. So
This
it
is
might be
why-
that in fact they are larger rings that are more stable than what you have shown.
Probably, yes.
Going back once more to your stripe structures, let's have a look at any of these stripe structures. Like this, for example, the structure D, that in fact structure D is even better, where you have space in between. If you calculate this surface formation energy dividing by the area, you take exactly the same structure, but you put it in the larger cell so that the spacing is bigger between the stripes.
Okay.
And you divide by a larger area. So necessarily the same structure with larger spacing will become more stable. And if you separate the stripes by the infinite amount, it will be the most stable structure.
Yes.
I have an impression that if your structure is not continuous, you should reason by atom. And if your structure is continuous and cover all the surface, you may reason by surface area.
Okay. Okay.
These things seem to be complementary. There was once discussion in the paper, in the early paper 2003, I think, by Kresse. One of these papers he has done with Netzer.
Okay.
Now, I like very much your summary of this chapter in this correlation. Yeah, well, just as a technical point, very clearly the relative stability of structure does not change as a function of induced chemical potential.
No.
So these plots are in fact not so very interesting. Whereas it changes radically as a function of oxygen chemical potential. So plotting the same thing as a function of oxygen chemical potential would show you a lot of crossing that would be very pertinent to identify the experimental conditions under which these changes could take place.
It's true. Yes.
Just another way of expressing the same results. But let's have a look at your final figure because I like it very much. The one where you show this one. The one before, sorry. It's very synthetic, and you have impression you kind of get an overview of all the systems. I like it very much. But it also shows that for some reason, the large majority of your structures are not stable for a reason, because they produce a rumpling that is negative and large, and charge transfer to the palladium substrate that is much too large.
Exactly.
So where this large charge transfer comes from?
Well, I didn't look into detail specifically on this part. I'll need to look into detail of why this happens on these structures.
Is it a question of the structure, or is it a question of stoichiometry? Because perhaps a little bit naively, I would imagine that palladium becomes negatively charged as to provide, as to evacuate electrons from the oxide if there's not enough of oxygen. Okay. But palladium, of course, can do it only in a limited way. So the oxygen deficiency cannot be too large.
Yes.
Would it be possible that where the palladium charge becomes really strongly negative, it's because your structures are very oxygen poor?
Yes, I think so. Yeah, you're correct. I think it's depend completely on composition of oxygen. And we have seen, for instance, this, at least I know that these compositions, they are really close to the EN203, so they're rich in oxygen. And also one of the most stable structures, this one, it's a bit lower in oxygen. So I believe this also take into account that when you have much lower content of oxygen, this may lead to the stabilization of these structures. I think so.
So this is informative because it tells you that it's probably not worth looking at the structures of these stoichiometries, but concentrate at the stoichiometries that produce only moderate charge transfer.
Exactly. Yeah, for instance, when someone would want to calculate a larger configuration of space, try to select structures that fits on this region and these compositions.
Now it might be a little bit provocative question, the last one for this part. So I make it a little bit provocative. But you have shown, in fact, that it is the cell 1/3 that produces the best results, the best structures. A bit surprisingly, but it happens. And in fact, the cell 1/3 is relatively small. You have what, 5 atoms, 6 atoms in it?
Yes, more or less 5 or 6.
So to optimize horizontal position of 6 atoms, do you really need to have genetic algorithms?
Yes, yes, it's true that the configuration space for the 1/3 is not so large. Usually we have some hexagonal tilings, and it's a good point that we should have applied this methodology for instance, for a 2x2 or try to select some others. But yeah, we thought about this after we have done the calculations. But it's a good point that we should select a bit better this 1/3.
I'm asking this question a little bit because we have had a case of similar case in our laboratory. Someone, an experimentalist, who was very happy to use the genetic algorithm and has told half-an-hour story about it to optimize the system with 5 degrees of freedom. So it was fun for him to do it, but you can question if it is really used.
Okay.
Let's move to the other part. So here I will join perhaps a little bit the questions by Anne, because at certain moment you tell that the adhesion between these periodic models, SSH and platinum, is very strong, and it is mostly due to the fact titanium atoms sit in the hollow sites. Later on, you analyze the cocaine model and you say that in fact, if you move titaniums around, it doesn't change much. So I don't know if this sitting in the hollow site is very important. We have looked at similar systems, didn't seem to be very important. And then this brings us to the question of your analysis. And the question if these are really the titanium-platinum bonds that play the most important role for the adhesion energy, or is it this charge transfer effect? I explain myself because often this may be confused. But perhaps you remember the works of people who were depositing metal atoms on thin layers of MgO supported by metal. And then were depositing the same atoms on the bulk MgO. And the absorption characteristics were completely different. Despite the fact that locally the bonds were exactly the same. But it turns out that there is a charge transfer from the adsorbate via the oxide to the metal substrate. So there was no bond creation. It was just the fact that electrons were shifted from the higher lying levels to lower lying levels by a kind of tunneling effect. So the gain was mostly the energy of state field. So are we really having strong bonds here? So if I put a titanium atom on the platinum surface, it would really create as strong bonds and as strong adhesion energy? Or it is rather this charge transfer effect that is related to the oxide aspect of this film, and the fact that in the film titanium is mostly honeycomb film. Titanium is mostly 3+, and if it has the occasion, it would like to become 4+.
Well, I think in this case, these are the bonds and the charge distribution, the charge that goes from the oxide and the substrate are fairly correlated, because first, when you do the COHP, here I didn't show, but to begin with, the COHP between strontium and platinum, it's very, very small. So that leads us to believe that their bond is not very strong, and also oxygen and platinum, also because oxygen is negatively charged and platinum as well on the first layer, so they repel each other. So this leads us to believe that what may play a role is the titanium bonds, and also there's this relaxation of titanium atoms closer to the platinum. And the charge transfer goes from the titanium to, especially the titanium to the platinum. So we have all these three elements that lead us to believe that this is the bond that actually is the most important. And it's, according to these calculations, they are quite strong. That's what I think of about this system.
Do you think that if you put just titanium atoms, it would produce as strong bonds and similarly strong charge transfer?
I don't think it's, I don't know if it, I think it will be strong as well, but I'm not sure about if it would be as strong as this one, because you have also the effects of oxygen and strontium. I'm not quite sure if what would be the correlation between the two.
Here this touches a little bit to this point, because you conclude relatively clearly that to get a better adhesion, you need to densify the network of titanium oxide, let's say that. So you need to have a larger amount of titanium. Is it the question of the amount of titanium? This joins the same point. Is it a question of the amount of titanium, or the stoichiometry should be also adequate? Because we have just discussed with your indium oxide that this charge transfer changes very strongly with stoichiometry. So if you want to have adhesion with a good charge transfer, strontium titanate and the substrate, is it just a question of amount of titanium, or you need to tune the stoichiometry as well?
In this case, you need to tune the stoichiometry as well. It's fairly complex because, well, you need to tune the stoichiometry. It also depends on how you build the tiny configurations. For instance, there is a very strong repulsion between strontium and strontium if they are too close. So the building blocks also construct in this matter. In addition, as we see that the amount of titanium must be quite high so that it first bonds with the platinum and stabilizes the oxide. So I think it's a combination of all these parameters that first stabilize the oxide and bond with the substrate. I think it's.
I wanted to ask you a question concerning, again, the stability, thermodynamic stability. In fact, we work quite a lot with this, so it's always very interesting for me. I have it at page 65. Hopefully, we have it at the same page.
Yes. Yes.
It is this. So in fact, you have compared the stability, you have done two things. You have compared the stability of thicker layer perovskites with the approximant, and separately perovskites with the honeycomb. Of course, in the context of this study, the question that remains a little bit not clear, what is the relative stability of honeycomb and approximant?
Yes. Yes, in this case, we have chosen in this case, two reactions. Well, this account for two equations. That is the decomposition of the thick perovskite layer to form either the approximant or either the honeycomb. But you're right. We didn't do the decomposition of the honeycomb to form the approximant.
Because optimistically, I would like to read from these two graphs that if you move the temperature arm, first perovskites transforms into the approximant, and then perhaps to honeycomb.
Yes, this is what we conclude as well from this. And I believe if we do the similar reaction, it would happen probably on the same temperature as the perovskites for the honeycomb. Or
one would hope to have it this way, although now we know that this relatively little dense approximant is probably not a good one, or not the best one. So if it does not appear as stable, perhaps it's not a big issue. It would be more interesting to do it with either cocaine or your new hand constructed approximant.
Yes, exactly.
But for me, in fact, the question or the little problem I have concerns the reference. Because of course, this stability, relative stability diagram would very much depend on what you choose as ingredients. So your periodic phase, it is relatively clear, there's no big choice. Your approximant, or you can choose one or the other. For change, I am not fully following your choice for the thicker perovskite film. For two reasons. First, I have the impression that it is oxygen rich.
Yes.
You have chosen two oxygen rich terminations, what makes the film overall oxygen rich.
Yes, you're right.
But judging by the experience we have just discussed with indium oxide and palladium, if it is oxygen rich, it does not produce the favorable structures.
Yes, actually, well, in this case, we have chosen these perovskite films according. Well, I've selected several terminations we selected the titanium termination, and also there's in fact only two terminations. This oxygen rich, which is a barium and oxygen, and the second one, which is only titanium. And we have chosen specifically this because the interval formation and the adhesive energy for this case were higher and stronger than when we had another configuration. For instance, when you have only titanium at the terminations. That's why we chose this configuration specifically. But we do not take into account this the fact that we have an oxygen-rich system that may lead to the stabilization of the interaction between the metallic substrates.
I think in general, thicker films tend to preserve the bulk-like stoichiometry.
Yes.
I think only in the monolayer films, substrate could stabilize something that does not have a bulk-like stoichiometry. But in the thicker films, if you force extra oxygen, it will always cost the energy. So this is one thing. The other thing, I don't know if you have looked at, because we have been working on this like 10 years ago, and since then it is a little bit forgotten, but I like to bring it so that it's not completely forgotten. You notice that along this orientation, this perovskite is composed of two types of layers, and one is charged negatively, the other is charged positively, negatively, positively.
Yes.
Do you know something specific concerning the terminations of these stackings of atomic layers?
Well, actually, well, of course, depending on the structure, it has this characteristic, but we do not take this into account in our case.
In fact, you can look at it as a little bit as the planes of the capacitor. So you have positive, negative, positive, negative, positive, negative, like a series of capacitors. And you probably remember from your lectures of electrostatics that you have an electrostatic potential that builds up and destabilizes the systems eventually. So in oxide, in fact, there are some orientations that are not very stable because of what we call surface polarity. That needs to be compensated, and it has a cost, which destabilizes this termination. So your film, I think, is both oxygen rich and polar. So probably there is a more clever choice that would stabilize it considerably, and then may shift its stability to much higher temperatures.
Okay. Well,
Probably something to be looked at.
Okay. Yeah, one thing that we have done, but it's kind of a trick in that I know you are aware of the dipole correction, that we apply a field in the different directions to have a negative charge in the end of the unit cell. Well,
this is a tricky point, in fact, because your film is symmetric. So many people say, okay, the argument I have just given that you have electrostatic potential that diverges with thickness cannot be applied because it's symmetric. So it is not polar. And this is not true. In fact, you have a divergence between the center of the slab and surfaces that goes symmetrically to the two surfaces. So the double corrections will not help.
I see. Okay.
To talk about something more sympathetic, your perspectives. You were saying about the molecular dynamics for phonon properties. What would be the technique of choice? Because you have these standard approaches to calculate phonons by displacing atoms, calculating force matrix, and so on. Some people do it by molecular dynamics. What would be your choice and why?
I think specifically when you try to study the bigger approximants, I would choose the ability molecular dynamics. If you want to study, for instance, it would be interesting to study in the beginning the stability of the first model, the Fuster model, and the second, the cocaine, by phonon calculations. I believe it would be possible because the unit cell it's big, but I think it's feasible. But my choice would be to stick with the ability molecular dynamics, especially because we also started to do this, but to try to see the stabilization of these oxides according to phasons. When you create a specific tiling block, and this tiling block create another one, there's some transformations between these blocks. And this would be possible to see by using this methodology.
Okay, thank you very much.
Thank you. Thank you very much for the questions.
Thank you. So now let's hear the questions of Céline.
Yes. Can you hear me?
Yes.
Yes.
Okay. So first of all, I would like to thank Emily for the kind invitation. As Anne, I encounter some strikes issue, so I am really disappointed not to be there in person. It's okay. Video is good, but it's not as a real PhD defense. So first, congratulations, Thiago, for your very nice manuscript. It was really, really interesting to read it, and you have a lot of very nice results.
Thank you,
and also congratulations for your presentation. It was a nice compliment to the manuscript. All of them was very clear and pedagogical, so it was really interesting to follow. So for the question, maybe I will start with a quite general question more than by curiosity. In your introduction of the manuscript, you speak about the property of barium titanate to be ferroelectric, which is a very interesting property of this material. But do you think you can observe some ferroelectricity in the system you report in your PhD?
Well, I'm not sure. It's quite it's quite complex to say. Well, the only thing that I can say is that we have a polarization of the surface on these systems, which may lead to ferroelectricity, but we are not sure if this is stable or not. If the real approximate phase actually has these polar moments or not. But well, in our calculations, we actually find this.
Okay. Yes, in general, you observe ferroelectricity in a seeker system. I think here you are too thin to observe some ferroelectricity.
Yes. Yeah, and well, I believe when they do calculations for the ferroelectricity on bulk barium titanite, they need to use bigger supercells so that you can see the polarization in various unit cells. And in our case, it's quite difficult to do this due to the size of our systems.
Okay. I had a second question, but it has already more or less asked by Anne. I was also surprised by the 3-layer system platinum slab you use for the cocaine phase. In general, even for very small molecules like carbon monoxide or very small one, with only 3 layers of platinum, the slab is too small to, let's say, absorb all the charge and geometrical effect of the adsorption. So as Anne already mentioned, I think it could be nice. I know that calculations are really expensive, but to try to check how the charge and the geometries evolve with maybe some larger slab.
Okay. Yeah, well, I can comment that in this case, we think that 3 layers of platinum would not be such a problem, because when we look at the forces of the less platinum layer, the forces are really small, and also the distortion on the second layer is not very significant.
Okay.
So I believe adding a 4th layer actually increase the overall calculation, their general properties, but it's not very significant, I think.
So maybe for the first system you use 4 layers, right?
Yes.
And did you check some influence on the 3rd layer, or?
Yeah, well, the influence that we saw is actually see the forces that we had on the 3rd layer when we allow them to relax. So since the forces were quite low, we considered that we could use only 3 layers.
Okay. Yes, I have also a question still for the sigma phases. So in your manuscript, page 67, you discuss about the rumpling, and you demonstrate that this is a cation which mainly interacts with the substrate. I'm used to iron oxides, and when you study the epitaxial growth of iron oxide on platinum, for example, you always observe a higher interaction with the oxygen termination of the iron oxide with platinum. So the reverse rumpling than the one you have. And you can observe very strong platinum oxygen bonds. So I don't think that the electronegativity of iron and titanium are so different.
Mm-hmm.
So how can you explain this difference of behavior? I don't know if you have some ideas about this.
Well, actually, I think this specific for the approximate phases, it behaves quite differently from when you have the bulk. especially because we see that the oxide is donating the charge. So that in this case, the transition metal, well, titanium becomes very positive. And this is why actually have an attraction between these two atoms, and the oxygen become more negative and they are repulsed above the surface. So I think it really depends on the structure or on the system that we are studying. Even though iron and titanium are quite similar, the chemical environments, in this case, I think it's very different.
Okay, yes, thank you very much. Finally, I will have some practical question with USpecs. I have also tried to use it a bit recently. So first of all, you did some stoichiometry variation.
Yes.
And at least up to the release 9 of USpecs, it was unavailable for the surfaces. So did you do this manually, or did you have a new or beta version in which you can do the composition variation directly from surfaces? Yeah, no, in our case, we used, we did it manually. We fixed several compositions. And we did use specs for all these compositions. We didn't use the variation, the automatic variation composition, but it would be much simpler to do this, I think. Yes, I know, and I have tried some beta version with Oganov, and it never works. So I was really curious to see if you have some solutions. But okay, you did like me manually. Okay. Yes, sorry, I didn't try it. And yes, also for another possibility you have in USpecs, you have the reconstruction possibility. So why you didn't try to do this instead of checking manually the 1/3, 1/5, and 1/7 reconstruction? Because with the automatic search of USpecs, maybe you could have found some reconstructions, some different reconstructions. Yes, yeah. Well, in fact, it's a great suggestion. We did this thin 1/3, 1/5, 1/7 because we had the experimental evidence that the structure was thin, was large in one dimension. Okay, but it would be really good to do this as well. Because this option works very well. Okay. Contrary to the composition. Okay. And also last question, I think it's on slide 35. You mentioned that you tried two, yes, this one, two different termination, the palladium and indium one. So this was for the surface region, why? Right? Yes. Okay. And the results you present in the most stable configuration, you observe both cases. You can observe some differences depending on the starting surface region, or it was more or less everything mixed? Yeah, in fact, well, I show here exactly the setup that we used, but in the end, I didn't show any difference because, in fact, we didn't find any. By choosing, you could simply choose the palladium termination, add indium and oxygen. It's the same, and you can even search better the configurational space by only using this. It's okay. It doesn't even matter. It doesn't matter so much in this case. Okay, so I think I don't have any more questions. Congratulations again. It was really a nice and interesting work. And congratulations. Thank you very much, Selim.
Thank you very much. So now let's hear Stefan.
Yeah, Thiago. First of all, thank you very much for this very nice thesis that you have put together here, especially for me as an experimentalist. it was a nice introduction into the reasons why DFT must consider these aspects and so on, without going into technical details. You brought me close to the topic that you had. And of course, you know that I was in parallel on the experimental side, hunting for resolving this quest whether our old model or the cocaine model is the correct one. And therefore, it was super interesting for me to follow your approach here and getting the arguments why indeed our model is an improper one and why indeed the cocaine is correct, giving the correct solution. I have a question regarding again about the stability arguments that you get out from the calculations. And if I got it right, then we can take the adhesion energy as the criterion to see what is the superior configuration for the system. Yeah, and in this regard, of course, the honeycomb structure turns out from your calculations to be the most favorable one of all.
Yes.
And I had a look to the 2020 paper of Mr. Goliakowski, and he calculated the empty titanium 203 honeycombs sitting on top of the platinum. And he did it for constraining the honeycomb unit cell to a 2x2 platinum subcell. It's the same procedure that you applied?
Yes, it's exactly the same. We use the same 2x2 cell.
Now he gave a number of 4.78 electron volts per formula unit as the adhesion energy. If I break it down correctly in your units of EV per square angstrom, it should be in the order of 0.18.
Yes.
And it's much different to what you got for the honeycomb with the barium on top, which is in the order of twice as much.
What is the number that you have?
So I calculated it from the 4.78 electron volt per formula unit, and the formula unit is the unit cell 2x2 unit cell of the platinum. So if I divide by the area, I end up with 0.18 EV per square angstrom.
Okay.
It is a factor of 2 to what you get when you add the barium on top. And this also adds to the question before whether there is some additional stabilization coming from more charge in the system. What is the role of the barium in the game over there? Which is obviously highly when stabilizing the honeycomb structure.
Yeah.
And maybe two more things to go. It's quite a long line. I would like to ask you to follow me. You have started here in the presentation also with a nice plot showing that the rumpling is intimately linked to the charge transfer in the system. And of course, if we now force the honeycomb to be a 2x2 on platinum, where it wants to be 2.15 times 2.15 in the experimental system, we maybe induce some rumbling into the system which is not present in real life. And then maybe we overestimate the adhesion energy in the honeycomb, why it comes as a favorable system as compared to the cocaine model of the sigma case. Can you argue a little bit how much these effects are?
Yeah, it's a good question. In fact, it's a bit hard for me to say because when we model the honeycomb structure, we do not try to see why this structure is stable. We only selected one of these structures to try to compare with the approximate structure that we have. So we have chosen one structure where we add one binding on top and compare this with our approximates. But I'm not quite sure about the reason why, if you add this binding, it could be more stable, how it distributes the bonds. I'm not sure.
And if the rumbling is so important, then maybe also the dipole moment related to the barium is then also a relevant part to it. And if we have forced it to a too high rumbling already between the titanium and the oxygen planes, then the barium should be much more separated from the platinum surface, as in the case for the approximates.
Yes.
How would that change or add to the game?
Well, just maybe I believe that when you add a lot of bodies, it changes a lot. For instance, what, as you said, it changed the adhesive energy. It also changed where it comes from on the top. But I believe it starts to destabilize a lot the system, especially when you add a lot of bodies. You start to have a lot of. First, you have that the body is not really bonded to the platinum, and also you have the charge repulsion between all the bodies. And no, I don't know.
If one wants to describe it more realistically, one would have to increase the slab that you use for calculations for the barium containing honeycomb. So if it is in real life 2.15 lattice parameter, you could maybe think of 5 units so that you then can put it onto an even number of platinum cells.
Okay.
Would it be computationally possible to do that? Because when you have then the 4 layers of platinum, it's quite a lot of atoms involved.
No, I think it's possible. We could do this.
That would be very interesting by how much the adhesion energy would go down then. Mm-hmm. Because what we really experimentally observe is that you can start from the barium decorated honeycomb, and when you apply heating and offer some oxygen, then you will do the conversion into the approximate phase. Mm-hmm. So indeed, the honeycomb is less stable than the approximate will be. But it will probably change this geometry of this. But just by a tiny little bit, you go from titanium to oxygen 3, where you have then, let's say, barium 0.5. You change it to barium 0.5, titanium 1, 2, oxygen 3.1. Just a tiny little amount. It's just because some larger pores need to be created, and there you add a little bit of it. So the stoichiometry is almost identical.
But when you see this cycle, you have a complete change in the structure, or you have a competition between these 2 phases?
So we can really, it's an on and off action. So we prepare the honeycomb covering the entire surface. We dose the barium to the amount we need, and then we do the annealing, and the entire surface is converted into the other network structure.
Yeah, I believe this is this may relate to how a phase diagram works. When you have a temperature and pressure, you can favor one type of system than the other. But it would be interesting to test, for instance, create some models on this honeycomb structure to test different configuration, barium distributed. Because for me, it's quite unexpected what happens on these systems. It's only tested that we can really see what's happening.
You tackled it a little bit by showing that you arbitrarily can choose different patches and ask why isn't that the favorable approximate structure in the system.
Yeah.
And you nicely illustrated that there's probably a bunch of more structures to be explored. What would you say is the key parameter to drive it into the one or the other structure? What makes the difference?
Well, maybe one of the most important things is, for instance, you cannot have 2 rhombuses too close, because you have barium that are strontium that are too close. And I think this repulsion is quite strong. So you need to have a specific distribution of these strontium atoms in the oxide.
What is the minimum, if you would go to the cocaine model, what is the minimum distance of 2 rhombs? So by which element should they be separated? Do you know that?
No.
Have you looked into it?
No, no.
Okay. Because then it comes out from the ring structure of the titanium. Yes, the rhomb is connected to a 10-membered ring, and you can only have another 10-membered ring next to it. That leaves the gap of a triangle. So they must always be separated. If you are on the playground of this titanium network, there you have limitations.
I see. Yeah, it comes down to what you have discovered on the stone wheels defects and transformations, that you have the formation and transformation of different rings. And I believe the strontium atoms, they accommodate according to how these defects are formed. And, well, it's fairly complicated to believe what's happening.
I would like also to come back to the question raised by Professor Gorniakowski, that if really the titanium density matters a lot or not, or whether this is a stoichiometry. And I think this is nicely discussed already in your thesis when you compare this square approximate, the strontium titanium oxygen system with the hexagonal one that you found here. Because there you had a plot in which you go very much down with the adhesion energy, but the stoichiometries of the two are almost indistinguishable. You have strontium 0.36 versus titanium and oxygen 158 or so, and then it is strontium 0.38. So there is within 1% or 2 that the stoichiometry differs, but you go then from the black one to the blue one. And the sigma phase approximant, then if you go to our own model, then it's natural why we are so bad in adhesion energy. It's just because of the low density of atoms. And there comes the point at which I am surprised that still the TFT says that this is a stable structure, where in the calculations you would see that it cannot be the true solution to the system. Is there some strategy you could apply to see when it explodes, for example? You did this annealing for the cocaine model. Did you do that also for our model? The old one? It must explode, it must fly away. Or...
No, which annealing? You mean the...
You annealed the cocaine sigma phase as reported here in the thesis to high temperatures.
Yes,
and you saw the ring opening and some transformations.
Okay, yeah.
What if you applied the same thing to the...
Yeah, indeed we did. Well, I didn't show the thesis, but we did this calculation as well. And the structure changes completely. It's, well, the first, because it do not have very compact atoms.
Yes. The
structure starts to deform and transform into something completely different. In contrast, the cocaine phase, it remains relatively stable through a really long time of the calculation.
Then I would have suggested that you include this decay of the structure also in the thesis, because this is then maybe the most obvious thing where you see that this is a long structure.
Yeah, you're right.
The low adhesion energy comes just from the low density of the material that you have.
Yes, you're right. Yeah, I think, as you said, the adhesive energy might be one parameter for the stabilization, but it's not enough to say if this is actually more stable than the other.
Did you try in the calculations to do the annealing also with the honeycomb structure?
No, I didn't try.
It would be interesting again to compare if the mechanism that opens the rings, if this is the same for the cocaine model or for the honeycomb structure.
Yes,
where you have different ring sizes.
Yeah, it would be. This is quite interesting. What we started to do right now is we took the big approximate and we are doing this annealing procedure. And it would be interesting to do this also for a supercell of the honeycomb structure, to see if, for example, if we put a lot of barium, we could actually see these stone wheels transformations to form to the initial form of the approximate phase. This could be one part of the perspective as well.
Yeah, okay. Then I would have a big question about the simulation of the SDN pattern, because it puzzles me a lot why the hell we find the density of states at the position of the alkaline earth metal atoms. I don't know if you have a backup slide showing the density of states of the system. You have...
no, I don't think I have.
So, for example, there's one on page 104 of the thesis. And so what I know about scanning tunneling microscopy is that you apply a certain bias, and then you collect all the current which is coming from the integration of the density of states from the Fermi level to the bias that you choose. Yes. And the other thing that I know is that it's exponentially dependent on the distance. So that means if there's some protruding atom or something which is 1 angstrom higher than the rest, we'll have a current of factor of 10 enhanced. What you show in the density of states calculation here is that titanium has the highest contribution at all over the energy range.
Yes.
And if I would do the integration from 0 to 1 or 0 to -1, I would have much more than a factor of 10 higher density of states coming from titanium.
Mhm.
Now in the true system, you have only a height difference of 500 picometers, so 0.5, no, sorry, 0.5 angstrom in between the titanium height to the strontium height. So they're almost on the same. That's why it's really surprising to me that you do not have significant signal coming also from the titanium. When you, for example, look into the pores of the squares, there must be 4 titaniums inside. Why don't you see anything?
Yes, it's quite surprising for me as well. But we try to do this calculation changing the bias.
Yeah.
And in some cases, for instance, here it's also possible to see some protrusion that might come from the titanium atoms as well. It's
good that you mentioned that. I would have asked about it also, because you see them, you can then say, okay, I find it in some tiling elements. So sometimes it's in a triangle, sometimes also it's in a rhomb that you have the 2 baryons, 2 strontiums here close together. And then in the perpendicular axis, you have also two maxima. And then you look to the neighboring rhomb and that looks different. So all that you say, I would expect holds for each tiling element similarly.
yes,
But it doesn't, it's not the case.
yes. At least when we use the Tesser-Hoffman approximation for this calculation, yes, unfortunately, we do not find this difference. It seems to me that in this approximation, the most important thing, well, first we need to have a non-zero density of states, and the heights. Height is the most important parameter to see the electronical features on this.
You have in this thesis, there is the other SDM image you calculated for the hexagonal approximant, but without the decoration of the centers.
Yes.
And in there you find systematic contrast variations here and there. So 2 pairs of the atoms in between these flower motifs are much brighter than the rest.
Yes.
What is different at these places? Is it the substrate underneath, that these are on top positions on the platinum?
Well, for this, this contrast happens only, well, in this case, I believe it's 1.5 volts for the bias.
Yes.
And
Yes, it is. Yeah.
so we try to compare exactly with the bias that were applied experimentally.
So I'm talking for yes, in the 103 in the bottom row. On page 103.
Yes. So yeah, you have this bright protrusions there.
Mhm.
So this only happens at this specific voltage, is 1.5. If you go to 0.5, it does not appear. And I try to look if it's actually the height of this atom that it's observed, but it's actually, I'm not quite sure of why it is right on that spot specifically for this voltage.
But just to make it more clear or more precise, you are here looking to the same entities. It's all the strontiums, and some of them have totally different contrast, although from the density of states calculations should be the same for all. There must be some ingredient that amplifies
Yes.
the tunneling current. And I was wondering whether this is coming from maybe the true geometric configuration towards the platinum, and maybe you have you open up some channels so that you look to the D states of the platinum shining through the oxide layer itself.
Yes. Yes. It may be a contribution of another electronic density.
Something which is highly localized.
Yes.
In contrast to all the rest.
Yes, exactly.
Okay,
Yeah, it
so
could be a nice solution. I'm not sure why this happens.
Okay. Finally, maybe you can. There was one question I had about the electrostatic potential. So on page 69 in your thesis, you go there in the figure 3 that you have these phi1 and the phi2 contributions far from the surface. Where do they come from?
Well, actually, okay, so the first phi1 is the electrostatic potential that comes from the surface of the oxide. So it actually, if you do the difference with the energy, the Fermi energy, so you have the work function. And on the other side, you have, well, since it's a symmetric slab, you have the surface of platinum at the bottom. So we have the work function in one side of platinum and on the other side of the oxide.
So that, okay, I see. That means I have to read it this way, that at 30 angstrom, then the slab repeats, and then I have the bottom of the platinum
Exactly.
again.
So here we have the vacuum region. And well, in this region, we have platinum. So
Yes.
in this side, what we're seeing is the platinum contribution. And on this side is the oxide contribution.
Does it mean that you can read out of the difference of phi1 and phi2 the work function difference of the two materials?
Yes, exactly. So what we can conclude here is that when you put the oxide on top, it decreases the work function of this system.
Yeah.
And you can measure exactly how much it decreases.
And that is strongly linked again to the dipole form from the oxide, and this is strongly linked to the rumpling. That means it's very crucial in the calculations that you get the rumpling right, and
yes,
that you have the most natural description of the system.
Yes,
you
exactly.
do not impose rumpling by a constraint to the smallest cell.
Yes, it's all connected to this parameter.
Yeah, thank you very much. It was my pleasure.
Thank you very much.
To look so deep into all your calculations.
Thanks.
Thank you. Let's hear now Anton. You hear us? Can you hear us?
Yes. Hello.
Okay. It's your
Can you
turn.
hear me? Yeah.
Yes, we can hear you.
Yeah. Okay. So I would like to join the opinion of other members of the committee and congratulate Thiago for the excellent work he have performed. So I, in my opinion, the thesis is very well written. The presentation today was very clear and easy to follow, and the amount of work that was performed in this 3-year period is really huge. So Thiago has visited me several times during his thesis in Ljubljana, where we had a lot of discussions, and so during that time I was able to see, to have the glance of his performance. So I have seen that he really has a very good, let's say, scripting skills, because I think in our profession as a modelers, these scripting skills and programming skills are such a plus that they are almost mandatory. Because if somebody wants to perform modeling and doesn't know how to do scripts, I think she or he will be at least one order of magnitude slower, if not more. And so now I have touched this business of scripting. And so, Thiago, you have written this Vulcano code, whose purpose is of managing or gluing different computational tasks together. So in a sense, to be kind of a manager of the whole computational workflow. And so here I have some question. This is kind of curiosity question. So yes. What does the name Vulcano stands for? Is it some name that comes from somewhere? Okay, I know what Vulcano is as a word, but maybe it is an acronym. And then maybe if you can explain us a bit about technicalities of this Vulcano. Obviously, it's written in Python, but probably it uses some libraries like MathGen, or is based on atomic simulation environment, or something similar. So can you describe a bit this code of yours, the Vulcano?
Yes, of course. Thank you very much, Don, for your question. Well, the name of the code actually comes because, well, first I like Vulcans, and it's more, if you imagine this type of script, you have like an explosion of calculation, explosion of results that you treat all at the same time. So this was my idea of why I chose this name. And well, the way that this code works is I think you're familiar with some other managers of scripting to launch and get the results, such as Ada. And I built this code specifically because at the beginning I did not have the scripting skills to use Ada or some more advanced codes. So I started something exactly for me from scratch that would be used in principle only by me for this type of system that we have for slabs and interaction at the interface. And the idea, basically, we use several different tools for this codes. Well, it's written in Python with aid of some shell scripts. It uses a combination of PyMagen, of IC, ISO, and many other libraries. And the idea is that you give as an input to the script, you create what's called an object, an atom object of IC. So you create a list of all the structures that you want to study. After you select which type of calculation you want to perform. For instance, you can select relaxation, you can select calculate the SM image, calculate the COHP, adhesive energies. You can do all these calculations at the same time, only by selecting one true or false. And you can do this automatically for 1,000 structures if you want. And in the end, you can also, it's more or less manual that you need to do in the end, you can also get the post-processing automatically. So basically, nowadays, the state of the art of this Vulkan code, you can put the structures, press one button, and get all the results for all the structures that you have. So this is more or less how it works and why I chose this name.
Okay, thank you very much for the explanation. So now I understand the origin of the name, because for me Vulkan was completely something that I could not understand why this code is called Vulkan, but the explanation that you have the explosion of calculations and the Vulkan explodes, that makes sense, yeah. And now, because more or less all of us that do modeling uses some kind of, let's say, manager for managing many calculations. And one of the advantage of doing that is when you do a mistake. And so maybe if you can comment this, so let me be more precise what I mean. If everything is done manually, you can do, let's say, stochastic, some mistake by chance, and this is very, very difficult to spot, because there will be, suppose that you are copying the input files and then you are editing the input files, and then at the given point you made a mistake, and then this is difficult to spot such a mistakes. But when you do scripting, if you do a mistake, these mistakes are typically of different type, because if you do a mistake in the scripting, then probably all the calculations are wrong. This is my experience. Yes. And then this is much easier to spot, because either it is correct or everything is wrong. And if everything is wrong, usually this is easy to spot because it goes nowhere. So do you have a similar impression concerning this issue?
Yes, of course. I have the same experience. And I can answer you with my story on the first year of my PhD. Because at the beginning we're selecting the full sigma model, and we did the first part of the work with several compositions, and we calculate. There were a lot of things that we need to calculate, and well, since I did not have much experience with VASP and didn't have much experience with scripting, I did basically everything manually and trying to learn by myself how to do, with Emily, of course, with how to do all the scripts. And in the end, I committed a mistake, roughly at the end of the year, that I saw that there is one part of the script that you need to put minus 0.05, right? If you put plus, you get something that you see the energy, not the forces. So at the end, I had everything done, but I had this one parameter that was false. So I needed to redo everything, all the calculations, only because of this one mistake. And I passed. It was so hard, my vacations, because of this, that I decided to start to do something more automatic and learn more things like this, because I really think that it's improve your life, because it saves time for you. It does not allow you to commit mistakes like this. So that's my experience on this subject.
Okay, thank you very much. And then the next question I had was more or less already discussed with the question of Stefan. So it was about the tiers of Hammond approximation of when you model the STM images. So this was more or less answered, but nevertheless, maybe just two small questions here. The one is the question of bias, because usually saying what is plus 1 volt or what is minus 1 volt sometimes is not very clear. So I would assume that for you, plus 1 volt means that you are looking at unoccupied states, right?
Yes, exactly. We have tested this before, and we're sure that it's the unoccupied states.
Yeah. Okay. And then the other is, but I think this can also be guessed from the caption, because you specify that you are looking at particular charge density, because basically we have two different modes of STM. One can do a constant height or constant current mode, right? But given the fact that you are looking at a particular value of the charge density, this would imply a constant current mode of the STM, right?
Right.
Yeah. Okay. Thank you very much. And then the last question, I think was already discussed before. This is about this palladium and indium. And here I'm curious because you used 1 times 3, 1 times 5, and 1 times 7 supercells. So this is 1 times something, right? And so here I'm curious why the choice 1 times something. Now, the choice can be based on two reasons. One is that there is some physical hint that the system wants to have 1 times n. The other choice would be you have to start somewhere, right? And so I'm curious what it is in this time, because later on during the discussion, you also mentioned that you were trying 2 times 3 and so on. So I'm really curious why 1 times n was used for this study.
Yes, in this case, it was because we had experimental hints that the structure is actually 1 times something. Actually, there was a hint that it was 1 times 7. So we started from this and we built some smaller models from this. But in fact, we should have expanded this to 2 by 2 or some other configurations as well.
Okay. Okay, thank you very much. So then this makes sense. It was based on some experimental evidence, and you choose it. You choose it for this reason. So thank you very much. Congratulations again for a very clear presentation today for very well written thesis. And I was in this point I would also like to thank to Emily for involving me in this cooperation, which I think was quite fruitful. So thank you very much. And now I would like to pass the word back to the president of the commission.
Thank you very much, Tom.
Thank you, Anton. So now I believe it is my turn to ask a few questions. Actually, there was already quite many of them, so I will just quickly ask some stuff. So at some point you have mentioned DFT plus U calculations, right? Mm-hmm. And if I remember correctly, you said that the U parameter that you have used comes from a previous work, right? Mm-hmm. But as you know, in this sort of calculation, I mean, the value that you input is quite important. Mm-hmm. So my question is a quite standard calculation, quite standard question in this case. Let's say if you change a bit the value of this parameter, how much is it going to affect your results?
Yes,
I mean, is it very sensitive, or does it matter or not?
Yes, actually, it's very sensitive, especially to the total energy in the end.
Okay.
So in the beginning, we tried to calculate this parameter for ourselves. For instance, when we decided to select a U parameter for a system that is very similar to ours. So for instance, we chose the work by Górkowski, that he has a system that were very similar. Mm-hmm. And I believe that it corresponds very well to what's to the closer that we could get to what could be a real simulation for our system.
Okay, well, okay. Let me rephrase my question. Let's say if you, I don't know if you tried this experiment, but let's say if you change the value by 10%, is it going to affect? I mean, I understand, of course, it's going to affect the numbers that you get, but is it going to affect the general conclusions that you got?
I don't think it would affect very strongly the conclusions, because the most important thing is to be consistent. But if you use one value for one thing, you need to keep following it for all the others. So we set all these parameters and we use this for our calculations. So I believe in our case, this was the most important thing. And since we are, well, this parameter, it affects especially the band gap and some other intrinsic properties. And since we were looking more at the difference in total energies and charge characteristics, I don't believe it affects so much.
Okay, good. Still on the DFT plus U part, I don't know if you know about this, but when you start this sort of calculation, there will be initialization of the. So you will have a density matrix. So if you apply this correction to d electrons, actually you will have two 5x5 density matrix. That are used in the course of the calculation, and they need to be initialized in a certain way. And actually, so you have used VASP, and in VASP they initialize them in a certain way. And actually, it appears that for some systems, the way that they are initialized, those density matrix, it matters in the sense that you can be stuck in some sort of local minimum, and when you do the self-consistent iterations, actually it cannot get out of this local minimum. So I was wondering if you are aware of this problem, and if you have tried. So it is not in the. I mean, if you read the VASP manual, it's not there. They don't talk about that because it is done automatically. But I was wondering if you are aware of this problem.
Yeah, I was aware when I was discussing with some colleagues that also use this DFT plus U. But in fact, we did not look into so much detail in our case. We've done exactly this. We've looked for a system that were similar, and we have fixed these values. So. Yeah, it would be interesting to look into more details on this, but I'm not quite sure.
Okay. Yeah, one more question actually still about this business of functionals. So you have mentioned the opt-PB van der Waals, right? And again, I mean, a similar question as the previous one, considering the value of U. Did you try some other functionals, and does it matter or not?
Yes, indeed. Well, I put the comparison between other functionals in the appendix of my thesis. So what we have selected several functionals, and we have tested specifically for the interperformation and cohesive energy for the important bulk system that we had, and we compared these values with the literature. So from this, we have selected one that was the closest to the literature. And also we had this, in our case, we added this van der Waals functional because we were not sure if the van der Waals forces on these systems were important or not. So we started from this because of these regions.
Okay. So, I mean, so the general conclusion is that, I mean, if you use a functional A, B, or C, the general overall conclusion does not change that much, right?
Yeah, I don't think it would change that much if you are consistent in this case.
Okay. One more question actually about so as you have shown and mentioned in your manuscript, you have used quite a lot the USPECs, right? With this genetic algorithm and so on. Actually, some years ago, I have tried myself this code, and so I'm sure now it's much better than it was at the time. But at that time, actually, I was quite disappointed by it, I have to say. So what I've tried at that time was quite complicated. I wanted to predict crystal structure of molecular crystals. So this was quite tricky, but at that time it didn't work very well. And I was not completely sure, and I want to have your opinion on this, that in fact using all this business of genetic algorithms, whether it was better or not than just generating randomly a lot of crystal structures. So just to write a small code with some constraint, of course, because you don't want the atom to sit exactly at the same position. And then just to generate, I don't know, 100 or 200,000 of structure, depending on the size of your system, just run all of them and collect all the results.
I think when you start from, as in our case, we start from 0, it's much simpler to use the genetic algorithm code because you do not know what is the local configuration that is the most stable or not. In this case, you can test really everything that's possible. You can really test well the configuration of space. And I'm not sure if you do this in a simple way in a script to randomly generate these structures. I don't think it would be quite accurate as these systems.
Well, actually, it depends essentially on how you do your random generation.
Yes.
I mean, if it is large enough, at some point you will sample all the configurational space. So so my question is, because the first step of the USPEX is also consists also of generating randomly some structure, and then there are these steps using genetic algorithms. Because actually why I'm asking this is, at that time when I was interested in this, there was another code developed by a guy in London whose name is Chris Picard, and he was doing exactly what I said, that to generate randomly a lot of structures, and his argument at that time, so maybe it's not valid anymore, because as I said, I'm sure this USPEX code has made a lot of progress in the meantime, but his argument was to say that at the end, the amount of calculation that you do with USPEX, so starting from randomly generated structure and going through all these steps one by one, so one generation, another one, actually it was maybe not so different, in the numerical work, than generating a lot of structures, really a lot, and just collecting the results. So I wanted to have your opinion on that. I really don't know, so it's just
yeah, I think, for instance, if you do this for a simple case, for instance, the 1x3, it's completely feasible to write for yourself something
because it's small, right?
Because it's small. But when you, for instance, the 1x7, the number of possible configurations is so huge that, okay, there are maybe like this is a brute force approach. You basically try everything. Or in the USPEX, I think it's a more intelligent way to try to minimize your efforts to find this. Because, okay, you start randomly, but then you create the next generation based on the best ones. And you have these variation operators they build the next generation based, like you select 2 structures and build another one based on the other one. So it's a more intelligent approach to reach the same point. So in the end, I think you have much less effort doing this way.
Okay. I agree that on the principle, it's supposed to be more efficient.
Yes.
But I was wondering about on a real case. But, okay, I think I have some other questions, but we can maybe discuss also later. So I think now Emily with some words to say, I'm sure.
I will not ask any question, just make a few comments. So first of all, I would like to thank all the members of the committee for their very good remarks and comments. So obviously there is still work to be done because all is not perfect yet, but we will try to improve what has been done so far. I would like to thank Ton as well for his warm welcome during the few trips we did. And and I would like to, so maybe I would like to tell the story with the coming of Thiago here at IGL. So Thiago was Thiago applied before the thesis to another group to do an internship during his master thesis, if I remember well. But it was not successful, and at the end it did not succeed in coming here. So it did not get discouraged, and he tried again for the PhD in another group. And so this time it was successful, and he arrived a few years ago. But unfortunately, the COVID was here a few months after. So we had time to make, I think, one trip in February, just before the COVID. And then the thesis, which was supposed to be, let's say, half-half with Ljubljana, was mostly done in Nancy, with a few trips to Ljubljana when the frontier opened a little bit. But still, Thiago did a lot of work through all these problems. So congratulations for that. So I think you are a very nice guy, very autonomous. So I congratulate you also for the Vulkan code, which was not so easy to develop. And I hope in the future you will so have the work you would like to have, and be able to have a good life with or without the calculations. Let's see what happens.
Thank you. So I think we have heard everybody. So now I will ask people to leave the room. I think the
Feel alive. I found no way. talk it out, now I don't know what to say. How'd we go from laughing every day to only smiling just to prove that we're okay? Falling, but we don't wanna tell ourselves we're falling. If I'm always a villain of your story, how we gonna make it out? I know that I'm better off alone. I don't even know what I'm fighting for. You can't love someone with a heart of stone. This is something that I should've known. Yeah, I love you blind, but I don't care. I'll say I'm fine when I lose my mind, but at least we tried. Yeah, I love you blind, but I don't care. I'll say I'm fine when I lose my mind. I love you blind.
Every step forward feels like a fall. Dancing on the edge, 'cause it's all that we know.
And everybody tells me I should go, but I would rather lie with you than be alone. I know that I'm better off alone. I don't even know what I'm fighting for. You can't love someone with a heart of stone. This is something that I should've known. Yeah, I love you blind, but I don't care. I'll say I'm fine when I lose my mind, but at least we tried. Yeah, I love you blind, but I don't care. I'll say I'm fine when I lose my mind. I love you blind. I was so blinded. I was so in my head. We tried to hide it, but we hurt ourselves instead. But all the pain and all the shame, was it worth it all in the end? And all the memories of bad scars can let you keep me in the dark. I know that I'm better off alone. My peace and war is what I'm fighting for. You can't love someone with a heart of stone. This is something that I've grown to know. I loved you blind, I didn't care. I said I'm fine. Now I look at you with open eyes. Yeah, I loved you blind, I didn't care. I said I'm fine when I lost my mind. Yeah, I love you.
But still it's better than in before. Everything is like you're outside.
At the meeting, I think it just started this morning because it was broken the two previous days. But,
Okay, everybody is back. So, Thiago, the committee has decided to award you the title of Doctor of the University of Lorraine. The committee has really appreciated your work and your presentation and congratulate you. Thank you.
Thank you very much. Well, thank you very much, everyone. First of all, thank you, Emily, for supporting me during all these 3 years. You have been really a great supervisor. Thank you very much for all your support. And in every case, you were always there to help me. So thank you very much. I thank you very much, Tony. You have been also a really great co-supervisor. I thank you very much.
Here's a glass of wine.
Thank you.
Yes,
Thank you.
enjoy your.
Congratulations. Cheers.
Cheers, Tony. No, thank you very much. It was really great when, well, the scientific discussions and all the skiing that we did in Slovenia. It was really great. And I think also all the members of the jury for accepting to be here and also online. Thank you all, everyone for being part of my committee for the great discussions. I really appreciate it. Thank you very much. And I thank all my friends, all the people that are here to watch, and also online. Any people, Seb, if you have me. First, Seb, thank you very much for all the help. I would not know what to do without you. And not only this, and you've always been a great friend. Thank you very much for everything. And well, I think all the people that are here to watch, it was really nice to present to all of you. And well, all my friends, I thank you very much for, well, all the support during these years, all the friendship, and thank you very much for everything. Well, I thank my mother for being here. She came all the way from Brazil to be here with me. Então, muito obrigado, mãe, por ter vindo. Eu te amo muito. Thanks a lot, Kata. Well, I think you. Well, just let me breathe a bit. Well, as maybe you have read from the acknowledgements, because another really special thing that happened during this time that I got married with Kata. So I really love you. Thank you very much for all your support during these years, and you are really special to me. Thank you very much. And well, that's it. Thank you all very much. Now to finish the celebration, I invite everyone to the small party that we have to close the IGL. So we're all welcome to come and have a party with us. Thank you very much.
Thank you.
Thanks. All the best. Thanks.
Congratulations.
Thanks.
Well, thank you.
after all.